So this note-taking guide that I've given you, I will post it on the course website as well. So if you want a fresh one for whatever reason, it'll be posted on the course website. These are the formulas at the top that we'll be using today, and I will give you these formulas on the final exam on your reference page. Okay, you don't have to commit them to memory, but I do want you to know how to use them. Okay, so if you've taken physics lately, some of this will probably be a review, and if you haven't taken physics lately, well, then you'll be ahead of the game for when you do. So we're going to do some problems first with the relationship in this first formula here. Does anyone know what C stands for? Constant. It is a constant, yes. It's the speed of light. And it is 2.99 times 10 to the 8th meters per second. Okay? This one is the Greek letter lambda. It stands for, does anyone know? Wavelength. And that's in meters. And then this last one is not a V, it's the Greek letter mu, lowercase, and it is frequency. And it's usually in hertz, which is seconds inverse. Okay, so the speed of light is equal to the wavelength times the frequency. Hence, you get meters per second, right? Because meters times seconds inverse gives you meters per second. So that's where those units come from. All right, so one of the big things that you need to make a note to yourself is that make sure that your units, right? Your units need to be in meters. So let's do this one together. A laser used in the treatment of vascular skin lesions has a wavelength of 532 nanometers. Calculate the frequency of this radiation. So we have to do a calculation, a little conversion, before we can plug into our formula. This is 532 nanometers. Can we use that in our formula here? We have to convert nanometers to meters. 1 nanometer is equal to what? I mean, 1 meter is equal to how many nanometers?
Plus 10 to the -6.
9, that's right. Nanometers times 10 to the 9th nanometers per 1 meter. 10 to the 9th, okay? You need to know that conversion. So how many meters would this be? 5.32 times 10 to the negative what? 8. 8 meters. Okay? Make sure that you convert nanometers to meters, because remember, for you to get units of meters per second, wavelength has to be in meters, so that when you multiply by seconds inverse, you get meters per second. Okay, so we want to know the frequency. So you can plug it directly in and then do the arithmetic, or you can rearrange it and then plug it in. It really doesn't make any difference to me. You're going to get the same answer either way. Wavelength times frequency. So that means that frequency is what? We divide both sides. All right, we're just plugging in. So 2.99 times 10 to the 8th meters per second, divided by our answer that we just got, 5.32 times 10 to the -8 meters. Meters goes away. We're left with seconds inverse as our answer, which is what we want. That's what hertz is. So 2.99 times 10 to the 8th divided by 5.32 times 10 to the -8. So we get 5 point, how many sig figs are keeping 3? 5.62 times 10 to the 15th hertz. All right, I'm going to pause the recording and let you try the next one. A laser used in eye surgery produces radiation with a wavelength of 6.4 times 10 to the 2nd nanometers. Calculate the frequency of this radiation. I'll pause the video and give you a chance to try that. All right, let's go over this one. So, I just made these numbers up, by the way. I don't actually know if that's the kind of laser used in eye surgery. I'm just making it up. All right, so we're given the wavelength. Wavelength is 6.40 times 10 to the second nanometers. And we want to know the frequency. So what do we need to do before we can do any arithmetic here? Can we leave our unit in nanometers?
No.
No. So we say 10 to the 9th nanometers in every 1 meter. So what is that answer in nanometers?
6.4 times 10 to the -8 meters.
Okay, so now we're solving for frequency. Which variable is that?
The mu.
Right. So we're saying, okay, let's divide. So C is a constant, right? 2.99 times 10 to the 8th meters per second, divided by 6.40 times 10 to the -8 meters. So we're left with units of hertz. That's what we want. So we know now the only problem we could potentially have is just typing it into our calculator incorrectly, which does happen. But if you show your work, right, that will help because then I can give you partial credit. So I got 4.67 times 10 to the 15th hertz, seconds inverse. Do we agree?
Shouldn't it be 6.4 to the -7?
6.48.
That's just like
I got it.
Yeah. Yeah, you're right. So then 7 there. So that would change our answer. So yeah, we just do the 14th. All right, I want you to try the next one. And this is a true statement. I didn't just make these up. Radio station 89.1 broadcasts at a frequency of 89.1 megahertz. And that's the conversion factor. What is the wavelength of the radio waves? So I'll pause the recording and give you a chance to try that one. All right, let's go over this one. This time we're solving for a different variable, right? Because I gave you frequency and I want to know wavelength. So, I mean, that's where the station number comes from. If you've ever wondered where that station identifier, the number comes from, it's not just a number that was pulled out of the air. That's the frequency of those radio waves. That's where it's coming from. So if you've ever wondered where the number comes from, it's not just arbitrary, that's the actual frequency. So can we leave that in megahertz? No, right? Because our formula is based on it being in hertz, not in megahertz. So how are we going to do that conversion? 89.1 megahertz. There's 10 to the 6th hertz in 1 megahertz. So, you know, the next time you stub your toe, you could say, wow, that megahertz. So what do we get for our answer?
8.91 times 10 to the 7th hertz.
Hertz is the same thing as seconds inverse, right? So we can plug that into our equation. So we're solving for wavelength this time. So we're going to divide both sides by the other variable. So 2.99 times 10 to the 8th meters per second divided by 8.91 times 10 to the 7th seconds inverse. Seconds inverse goes away. So we're left with meters, which is what we want. 2.99 times 10 to the 8th divided by 8.91 times 10 to the 7th gives us a wavelength of 3.36 meters. It's the wavelength of those radio waves. Based on if you know anything about the electromagnetic spectrum, would those wavelength be expected to be dangerous? That's a big, whopping, huge wave, right? I mean, if it was dangerous, we'd obviously all be in trouble because that's broadcast right down the hallway. So no. Not dangerous waves. Not dangerous waves. Questions on how we do those kinds of problems? I know there'll be some like that on your homework on this. So. All right. Let's go into some fill in the blank. So when you take physics, you'll probably spend a lot of time talking about the history of the photoelectric effect, and we're really not going to go into great detail on the experiments itself. We're just more interested in what the photoelectric effect taught us. And it taught us that light and all electromagnetic radiation is a stream of particles called, does anyone know what they're called? Photons, that's right. Photons. And that all matter has both wave and, does anyone know the other? Particle properties. So all matter has wave properties, in other words, it's got a wavelength. All matter has particle properties. So you behave like a wave, you also behave like a particle. But do you behave more like a wave or do you behave more like a particle? Let me just ask you, are you really big or are you really, really tiny? You're a large macroscopic object, right? Your wavelength is not contributing a whole lot to your motion, right? If you talk about Newtonian physics, your wavelength isn't really contributing to how you move. Someone picks you up and throws you through the air, right? You're going to behave more like a particle than you are a wave, right? You have a large mass, your wavelength is significantly smaller than your mass aspect. However, when we're talking about an electron, right? Electrons behave more like waves than particles. So light behaves as if it has mass. So it's, because it's got both wave and particle properties, it does behave as if it has mass. So you can study that in greater detail in physics. I mean, you think about black hole physics, right? Light bends toward a black hole, that's behaving as if it has mass. There's a lot of ways that light behaves as if it has mass. We're not going to get into a whole lot of detail in physics in here because this isn't physics, this is general chem. Just want to give you some basic information on the theory behind the Bohr model, because the Bohr model is based on the photoelectric effect and some of the information that we obtained from that. All right, I'm going to scroll back up to our equations because we need to define a couple more of our variables. So we're going to scroll over to this one right here. All right, so this is energy. Energy, and it's in joules. This is Planck's constant, which is 6.626 times 10 to the negative 34th joule seconds. And this is still frequency, which is still in seconds inverse or hertz. Okay, that's how you get joules, because when you multiply joule seconds times seconds inverse, that goes away, gives you the joules. All right, I will give you Planck's constant on your reference page on the exam. You don't have to commit it to memory. And just like I'll give you the speed of light on your reference page. You just need to know when to use it, how to use it, how to plug it into your calculator. All right, so this is what we're going to do right now. We're going to get to this part in a second. Oops. We'll do this version of it in a few minutes. Right now we're looking at this, because you can calculate delta E this way, or you can calculate delta E this way, depending on what information you have. Okay? So does everybody have our variables defined here? Planck's constant, frequency in hertz, and this is energy in joules. Are we good on those variables? Again, I'll give you Planck's constant on an exam. Although after you use it a few times, maybe you'll commit it to memory just from repetition. All right, so let's go back down to where we were. Let's do some photon problems. Calculate the energy of a photon with a wavelength of 5 times 10 to the 4th nanometers. All right. So we've got, we don't really need to put the delta there yet because we haven't talked about changing energy levels at the moment, so you just leave it as E. Planck's constant times frequency. All right, E is what we're solving for. So it's just 6.626 times 10 to the negative 34th joule seconds times the frequency. Oh, now I'm in trouble. Was I given frequency? No, I wasn't. I was given wavelength. So what do I have to do first? I have to turn that wavelength into a frequency, right? So let's go over here and do a side calculation. What formula would I use to get frequency? Would have to use this one, right? To get frequency?
Yes.
So frequency would be this. Can I plug in nanometers? Can I plug nanometers into this formula and type it away and be done? No. What do I have to do before I can plug into here? So I've got to go back and either another step.
Convert it to meters.
Convert to meters, right? So 5 times 10 to the 4th nanometers, 10 to the 9th nanometers per meter. So what does that give me as our wavelength in meters? 5 times 10 to the negative what? You're just subtracting your exponents.
The -10.
Negative what? It'd be fifth, right? Because when you subtract it, when you divide exponents, you just subtract them, right? So 10 to the 4th minus 10 to the 9th gives you 10 to the negative 5th. Now I can plug that in. So that's 2.99 times 10 to the 8th meters per second divided by 5 times 10 to the negative 5th meters. So now I've got a value that I can plug in. 2.99 times 10 to the 8th divided by 5 times 10 to the negative 5th. So now I've got a value I can plug in. 5.98 times 10 to the 12th seconds inverse is what I got. Did you? All right, so now we just multiply that by Planck's constant. 6.626 times 10 to the negative 34th. Joule seconds times seconds inverse makes that go away, so that gives me my unit in joules. So 3.96 times 10 to the negative 21st joules. Is that a lot of energy? Not really.
Very little.
All right, do we see how to do this? You have to take a step backwards. Because if you just start trying to plug in here and you go, oh, I'm missing something, right? We have to first calculate frequency and then plug frequency in. Okay, because if you just try to jump straight to here, you're going to get stuck because you need to have frequency in order to keep going. So calculate frequency first, then plug it in. So why don't you try the next problem? I'll pause the recording. Calculate the energy of a photon with a wavelength of 52 nanometers. And that's coming from the UV region of the electromagnetic spectrum. Pause the video and let you try that. All right, calculate the energy of a photon with wavelength of 52 nanometers. So we can't directly plug into our equation of goodness. Oops. Wrong variable. Planck's constant times frequency, right? We can't plug into there because we're missing a piece, right? We don't have frequency yet. So what do we have to do before we can plug into our energy equation?
Gotta find
We
frequency.
have to find the frequency, right? So let's convert nanometers to meters. 52 nanometers, 10 to the 9th nanometers per meter. So what does that give us? 5.2 times 10 to the negative 8 meters. All right, now which formula are we going to use to get frequency?
C equals L to
Rem to V. Right, so that means We've got to figure out frequency. 2.99 times 10 to the 8 meters per second divided by 5.2 times 10 to the negative 8 meters. That gives me an answer in hertz. So 2.99 times 10 to the 8th divided by 5.2 times 10 to the negative 8. We'll carry out an extra decimal place. We can round at the end. 5.75 times 10 to the 15th hertz. Now we're ready to plug in, right? So 6.626 times 10 to the negative 34th joule seconds times 5.75 times 10 to the negative 10 to the positive 15th seconds inverse. So multiply that by Planck's constant. And we've got two sig figs we're keeping. So 3.8 times 10 to the negative 18 joules is what I got. Do we agree? Any questions on how we do these kinds of problems? Problems with these? No stoichiometry, right? You can always say that. Well, at least it's not stoichiometry. All right, let's talk about the Bohr atom. Let's actually talk about the Bohr atom itself. There we go. All right, Bohr model. Get my cursor out of my face. All right, need a new marker because this is wrong chart. Okay, you've probably seen this in high school or your previous science classes. Bohr's model of the atom has the nucleus, right? That's the nucleus. That's your protons and electrons. Not protons and electrons, protons and neutrons. And then what does Bohr's model have around it? These nice, pretty circles. Right? And so here would be an electron, 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 electron. Okay, these are, each level is called an orbital. That's what they're called. And each orbital has a number associated with it. So this first one is called n equals 1. N equals 1 orbital is called ground state. Okay, so then the next one will be n equals 2, the next level will be n equals 3, the next level will be n equals 4, et cetera, et cetera, et cetera, et cetera. Okay? So each energy level you go out just has a higher value of n going out and out and out and out. Okay, they're nice little circles. You might have heard it called in high school the planetary model. Even though the planets orbit the sun in ellipses, not circles, that's beside the point. Right? You might have heard it called that in high school. In the Bohr model, each orbital has energy associated with it. So ground state is the lowest energy. So it takes the least amount of energy to occupy n equals 1. Just like if I said, all right, which takes more energy for you to do? Lay on the couch and do nothing, or get on the treadmill and run, right? Laying on the couch doing nothing, that's ground state. That is you at your lowest energy level, right? Running on the treadmill, that'd be like way up there, right? So each level you go up is higher in energy than the previous one, okay? And energy must be put in. Energy must be put in to go up in energy level Right, so energy has to be added to the electrons to get them up to the next energy level. Because it takes more energy to be at n equals 2 than it does to be at n equals 1. Right? Which is like, if you got to go work out, you're like, oh, I don't want to get off the couch. You got to overcome that activation energy to get up and go, right? Something's got to motivate you to get up off the couch and go run on the treadmill. So you can think of that in terms of human relationships. And then when you go back down to energy, when you go down an energy level, energy is released when the electron goes down in energy level. So it takes energy to go up, but you get that energy back when you go back down. Okay? This is the Bohr model. This is not the currently accepted model of the atom. You still see it used in textbooks and on t-shirts and in lots of places, but this is not the currently accepted model, so just make sure you know that. Not currently accepted model. But the reason we study it is because it gives us a lot of insights that led to the currently accepted model of the atom. But just so you know, Bohr's model is not the currently accepted model of the atom. Okay, have we seen this before or some variant of it before? Yes. You might have seen the Rutherford model before too. That's the one where their orbits are all kind of random. That's Rutherford's model. All right. So just a quick review. This was technically in the material from like week 2 of the class, but I know you've probably thought about other things since the second week of this semester. So let's do some calculations involving Bohr's model. So go back up to our formulas. To find the amount of energy associated with a particular orbital, write this N right here, refers to the orbital. So N equals 1, 2, etc. Right? So if we're talking about the N equals 1 energy level, N equals 2, N equals 3. Is there such thing as N equals 0? No, there's not. All right, so the energy associated with that particular orbital is just this constant divided by the orbital number squared. Okay? Obviously, there would not be N equals 0 because that would be undefined. So if I ask you what amount of energy is associated with N equals 3, you just plug in N right here, and you'd be off to the races. Okay, so that's pretty easy. I think I've got one sample problem in your note-taking guide on this, just because it's not that bad. Yeah. What amount of energy is required for an electron to occupy the N equals 3 energy level in a hydrogen atom? So N sub 3, because that's not N sub 3, E sub 3 is negative 2.18 times 10 to the negative 18, right?
Yes.
Yes. Divided by 3 squared. So 2.18 is 10 to the negative 18 divided by 9. So that is 2.42 times 10 to the negative 19 joules. Do we agree?
Would be negative.
Oh, negative, yes, negative, thank you. Okay. Now, when we talk about these kinds of things, if you're calculating, well, we'll get back to this in a couple of minutes. So actually, I'll just wait until we get to the next formula. But if you are wondering why this is negative, that's the amount of energy it takes to completely remove it, right? So that's where, if you're wondering where that negative comes from. Let's go on to the fill in the blank. I've already mentioned this. I wrote it on the Bohr model stuff. When an electron transitions or moves or is promoted or whatever, Jumps, okay. When an electron jumps, although jumps implies that it's spontaneous, but that's okay. When an electron jumps from higher to lower energy levels, energy in the form of light is, when it goes from higher to lower, it's released. The wavelength of this light determines its
Frequency.
well, that's true too, but that's not the word I was looking for. Color, right. When you were in high school, did you do the flame test experiment? I did. When I teach introductory chemistry, we do that experiment. You take a little sample, you stick it in the flame, and then the flame turns green or fuchsia or blue, right? What's happening there is you're adding energy to those electrons. They're jumping up in energy level. They can't stay there, though. They're going to fall back down to where they were. And when they fall back down, that light gets released, and then the characteristic color is coming from the wavelength of that light that's emitted when it falls back down. So you're exciting it, it's getting promoted, and then it goes, ooh, I can't stay here, it falls back down, releases that light, gives you the color. Okay? So let's go back to the top to our formulas. We've got one last formula to discuss. It is the other version of delta E. All right, so we just talked about this version of it a second ago. Let's talk about this version of it now. Negative 2.18 times 10 to the negative 18th times 1 over n final squared minus 1 over n initial squared, right? So this is the final orbital, and this is the initial orbital. So if it falls from n equals 3 to n equals 2, right? 2 here, 3 here, right? It's always final minus initial. That's why this is delta. Okay. Technically, the delta wasn't needed when we did this version because there was no change. But now there is a change because you're going from change in energy from being in this position to this position, well, this position to this position. Okay? And this can come out to be negative. Okay? This can come out to be negative. Negative delta E is energy released. And positive delta E is energy required. Right? That's energy you'd have to put in. That's energy you get back. Okay? Just like our sign with Q when we were calculating calorimetry. It's the same thing. This is energy being released. This is energy that has to go in. All right, let's do some problems involving this. Kind of tie it all together. All right. An electron in a hydrogen atom transitions from n equals 4 to n equals 3. This question has 3 parts. What energy is associated with this transition? All right, so delta E is equal to negative 2.18 times 10 to the negative 18th times, let's decide what's final and what's initial. Final equals what? 3. And initial equals 4. So 1 over, it's always final minus initial, 3 squared minus 1 over 4 squared. So let's do that arithmetic. So 1/9 minus 1/16. Hold on, I typed it wrong. 1/9 minus 1/16. All right, now times 2.18 times 10 to the negative 18. All right, I got, let's carry out some extra digits. Well, there really aren't any sig figs to worry about here because that's not a measured value. 1 point, let's just say 0.6 times 10 to the negative 19th joules is what I got. Negative. Negative. Do we agree? Okay, is this energy that must be added, or is this energy that is released, removed? How do you know? Which one is it? You're starting out, here's n equals 4, going down to n equals 3. So, is this energy that's going out or must be added in?
Going out.
This is energy that's released, right? This is energy released. And how do I know? Because what?
Negative.
Right. Negative delta E indicates energy release. All right, let's do part C. What is the frequency of that light? How will we solve that problem? First of all, let's revisit our formulas. Which formula involves frequency? So this one,
C equals,
that one,
doesn't matter.
okay. What else involves, because we don't have,
E equals your H of your mu.
Planck's constant
Yeah.
times frequency. Which one are we going to use?
Planck's constant.
Right, because we're going to use Planck's constant times frequency. So, can we solve for frequency?
Yes.
Divide both sides by Planck's constant, and we get our value. So we take our value, negative 1.06 times 10 to the negative 19th joules. Divide that by 6.626 times 10 to the negative 34th joule seconds. Joules goes away. We're left with units of seconds, which is the unit of frequency. So 1.06 times 10 to the negative 19th divided by 6.626 times 10 to the negative 34th. Drop the negative, because can you have a negative frequency? That doesn't make sense, right? So we just drop that negative. So I get let's just go with 2 sig figs. 1.6 times 10 to the 14th hertz, which is the same thing as seconds, of course. Drop the negative because you can't have a negative frequency. What if I asked you what's the wavelength? Could you do that?
Now we can.
You'd go back one more step and solve for wavelength here. Right? So if I did happen to ask you what's the wavelength of that, or maybe I gave you a chart of all the colors and you had color and wavelength. Could you figure out the color? If you calculate wavelength, you could, right? Because that's a easy thing to look up on a table. How do we feel about this? Feeling pretty good? Did I ask about wavelength on my handout? No, I didn't. But if I did, because I mean, right, I could. All right, the next one's for you to do, so let me pause the recording. Electron in a hydrogen atom transitions from n equals 1 to n equals 3. What energy is associated? Is this energy that needs to be added or is it removed? And then what's the frequency of that light? Pause the recording. Since I'm the teacher and I can do this, let's go ahead and add it, just for good practice. What, I don't know why it's underlined. What is the wavelength of the light emitted / removed? Go ahead and throw that in there too. Now pause the recording. Things I do for you guys, right?
Appreciate it. Much appreciated.
Okay, so let's go over this one. N equals 1 to n equals 3. What's the name of n equals 1?
The ground.
Ground state, right? So you're at n equals 1, you end at n equals 3. So are you going down or are you going up?
Going up.
Going up. So final is n equals 3, initial n equals 1. Okay, so delta E, negative 2.18 times 10 to the negative 18th times 1 over, what's the final state? 9. And what's the initial state? 1. Because 1 over 1 is 1. So I got a negative of a negative gives me a positive number. 1.94 times 10 to the negative 18th joules is what I got. Do we agree?
Yes, correct.
Okay, is this energy that must be added or is this energy that's released? How do you know?
Added.
This is energy that's added. And then how do you know?
Because the change of V is positive.
Right, to go up in requires energy. And you could also look at the sign of delta E, right? This is a positive delta E. Reflects that. If I want to go run on the treadmill, I have to get up off the couch, right?
Yeah.
Okay. What's the frequency of this light? What formula are we going to use here?
E equals H.
Planck's constant times frequency. So to get frequency, it's just energy divided by Planck's constant. So take my answer from above, 1.94, 1.94 times 10 to the negative 18th joules. Divide that by Planck's constant, 6.626 times 10 to the negative 34th joule seconds. Joules cancel, I'm left with seconds inverse. 1.94 times 10 to the negative 18th divided by 6.626 times 10 to the negative 34th. I get 2.93 times 10 to the 15th hertz. Do we agree?
Yep.
Do you agree? We're not really worrying about sig figs because we're not measuring any of these values. So if you had rounded that to 2.9, I wouldn't have marked you wrong. That's not going to make a difference. How do I get the wavelength?
C equals tilde.
All right, so wavelength is this scenario, right? So C is a constant, is the speed of light, 2.99 times 10 to the 8 meters per second. And frequency, we just got 2.93 times 10 to the 15th seconds inverse. So we are left with meters. So 2.99 times 10 to the 8th divided by 2.93 times 10 to the 15th. I get 1.02 times 10 to the negative 1, 2, 3, 4, 5, 6, 7 meters. If you want to convert that to nanometers, that would be 102 nanometers. Right. Do we agree on this one?
Correct.
Could you look up that value to see what color it is? You can look up that color. Figure out what color that is. Of course, that's light you have to put in, not light that you get back.
Yeah.
All right. How do we feel about these kinds of problems?
Wonderful.
Wonderful. I like that. Any questions? All right. That's where we're going to stop with Bohr. We'll pick up with the quantum model.
Next 2 hours today.
You sure could.